So I have again come back with the remaining part of the magnetism chapter. In the last video I had at the end I had just drawn the hysteresis loop. So it is basically on the y-axis you are plotting the magnetization, on the x-axis you are plotting the magnetic field H. So this this kind of curve comes, that is the shape of S. So from here, this is the point, that is the origin, is the point where the magnetic field is 0. So gradually you are increasing the magnetic field. So here what happens here at this position, the it is like this actually. This H is equal to 0. The magnetic domains are in this form, okay, at this position. So now when you are increasing the magnetic field, gradually what will happen? See, just here only it is given, that is weak magnetic field. The the magnetic domain whose dipoles are in the direction of the magnetic field, that domain will gradually increase in size. That is domain wall motion. That is here there will be, in this region there will be domain wall motion, okay. Domain wall motion, and gradually what will happen, the domains will increase in size, and then here in this region there will be the rotation of the domains, that is ultimately all these domains will rotate now. Suppose this is the direction of the field, okay, this is the direction of the field. Ultimately here it is in this direction, it is in this direction, this is in this direction. So ultimately what will happen at very high fields, the domains will rotate itself, that is the dipoles will rotate itself towards the direction of the magnetic field. So it will happen at a higher point of the magnetic field in this region, okay. So ultimately here what will happen, here this will correspond to actually this part, this will correspond to actually this part, okay. So here what will happen, here all the domains will be oriented along the direction of the magnetic field, okay. So this is called, means that is this is means after this, if you increase the magnetic field more, the magnetization will not increase, it will be same. Because why? Because you have got saturation here, you have got saturation. What do you mean by saturation? Saturation means that there are certain fixed number of dipoles here, fixed number of dipoles. Now if all the dipoles have got arranged towards the magnetic field, if you increase the magnetic field more, what will happen? There are no more dipoles left. So when no more dipoles are left, all will be oriented along that direction. So if you increase the magnetic field more, there are no more dipoles left, so nothing will happen. Magnetization will not increase. How will the magnetization increase? Magnetization increases when the dipoles are arranged towards the magnetic field. So if you increase the magnetic field more now here, after this, say at this position or this position, what will happen? There are no more domains or left to align themselves, or there are no more dipoles also left. So all have aligned towards the magnetic field, okay. Here all the domains are aligned in the direction of H, okay. So no more domains left, okay, to be aligned. You can write it later. This is there is my very cramped space here. So no more domains left to be aligned, okay. So this is called as saturation. This is denoted as ms, saturation magnetization. Okay, this is denoted as ms, saturation magnetization. That is, what is saturation magnetization? That is here the value of the magnetization, which is means after which if you increase the field, the magnetization doesn't increase more. That is called as the saturation magnetization. Okay. The value of the magnetization after which if the magnetic field is increased, there is no increase of magnetization is called saturation magnetization or ms. Okay, or ms. Now what is happening here? Now you are decreasing the magnetic field. Now you are decreasing the magnetic field in this direction. Now you are decreasing the magnetic field. Okay, you are decreasing the magnetic field. So what will happen? So if you decrease the magnetic field, the magnetization will also decrease definitely. You are decreasing the magnetic field in this direction, in the opposite direction. Okay. So now what will happen? Now the if you decrease the magnetic field, magnetization will gradually increase. Now the interesting thing is that the main point of this hysteresis loop is that if you increase the magnetic field, when the magnetic field in the opposite direction it comes to zero. So generally what will happen for paramagnetic materials, what will happen if you decrease the magnetic field, the magnetization will also become zero. But in case of ferromagnetic material, what happens? The magnetization doesn't become zero. Okay, there is a finite value of magnetization at magnetic field 0. Okay, this is called as mr. This is called as mr. mr is called as the remnant magnetization. mr is called as the remnant magnetization. mr is called as the remnant magnetization. Okay. Remnant magnetization or residual magnetization. Remnant magnetization or residual magnetization. Okay, this is called as remnant magnetization or residual magnetization. So what is this actually? So that is this is only hysteresis. Hysteresis comes from what? Hysteresis comes from history. Hysteresis comes from history. Okay, so this means what? That when the magnetic field is decreased and it becomes zero, the magnetization is not zero. It retains some of its magnetization. That is, it remembers the history of it. So that is why this property of hysteresis is used in memory devices. Okay, this property of hysteresis is used in memory devices. used in memory devices. That is, it remembers the history. It remembers the history. Okay. So when you are decreasing the magnetic field, when the magnetic field becomes zero, the magnetization doesn't become zero. It retains some of its magnetization. This is called as remnant magnetization or residual magnetization. So this is the property of ferromagnet. In case of paramagnet, in case of paramagnet, in paramagnet, uh, when H is zero in the negative direction, M will be equal to 0. Okay, but in case of ferromagnet, this is not the case. Acha, now what will happen? Now you are decreasing the magnetic field more. Now you are decreasing the magnetic field more. Okay, like this you are decreasing the magnetic field. So then what happens at this position? At this position, what happens? This position, the ultimately the magnetization comes out to be 0. Okay, at this position the magnetization comes out to be 0. This is called as the HC or coercivity. This is called as the HC or coercivity. Okay, this is called HC or coercivity. So what is the coercivity? Coercivity is this much. This value is called coercivity or HC. Okay, so what is the coercivity? Very simple. It is the magnetic field in the negative direction required to remove the residual magnetization of the material. Okay, the magnetic field in the negative direction required to remove the residual magnetization of the ferromagnetic material is called as the coercivity or the coercive field. Okay. The magnetic field in the negative direction required to remove the residual magnetization required to remove the residual magnetization from the material is called the coercivity or coercivity or coercive field. Okay, it's called as the coercivity or coercive field. Now what will happen? Now if you now you are increasing the magnetic field in the more, you are increasing the magnetic field more. So actually this thing happens. So gradually the magnetization decreases, and ultimately here again also in the negative direction it attains saturation. Here in the negative direction it attains saturation. So here what will happen? Here you will have this kind of thing. Here exactly this kind of thing, and the magnetic dipoles in exactly in the opposite direction you will have. So how will you have this? You will have like this. So like this. exactly like this it will happen. And here here this situation. Okay, so exactly see here in this region, that is positive magnetic field, what happens, the magnetization are rotated along the dipoles are directed along this direction, whereas in this position, that is exactly in the negative, this is, if this is say if this is say plus 1.6 Tesla, this is a minus 1.6 Tesla. Okay, so here what will happen, here the same thing will happen but in the negative direction, that is this will be in this direction. So here I have drawn these, the atomic dipoles is in exactly opposite direction, they will be oriented. Okay, so this is the hysteresis loop. Now you will have the applications of hysteresis loop. Applications of hysteresis loop. Okay, so what are the applications of hysteresis loop? Now hysteresis loop are basically, you can classify it into two types, that is the one which I had drawn in the last page, like this. This is called as the hard magnetic material hysteresis loop. Hard magnetic material. And this is called as soft magnetic material. So based on area of the hysteresis loop, magnetic materials are classified into two types. That is the area of the hysteresis loop which will be very big, very big area, those are called as hard magnetic material. Okay, and the area of the hysteresis loop which are very small, those are called as soft magnetic material. Okay, so where are these materials used? That is I mean hard magnetic materials means area is more. Okay, hard magnetic material area is more, so hysteresis loss is more. Okay, so this like this here the how does the hysteresis work? At the beginning this is like this, then ultimately the entire domain rotates along the direction of the magnetic field, and again from there it again comes back to this position. So this huge energy is lost. Okay, for what means work is done, that is the domains, what these domains rotation and movement, the work is done, so this work leads to loss. This is called as the hysteresis loss. Okay, so the so this hard magnetic material, that is the loss for which the loss is more, hard magnetic material. Okay, hard magnetic material for which the hysteresis loss is more. Hard magnetic material will have definitely the retentivity high, retentivity and coercivity will be high. Okay, and since their retentivity and coercivity are high, they the retentivity high means they definitely they can be used in memory devices. Okay, so they can be used in basically permanent magnets are good memory devices. Okay, they can be used in permanent magnets, they can be used in memory device, that is hard disk, CDs. Okay, then the hard magnetic materials are used in your telephones, loudspeaker. Okay, telephone, loudspeaker, they are used in the telephone, loudspeaker, etc. Then materials where you need this thing, that is permanent magnets. There are materials where you need permanent magnets. Example is galvanometer. Okay, example is galvanometer. So example of hard magnetic material are what? Example of hard magnetic material is alnico. Okay, alnico, that is aluminium, nickel, cobalt alloys. Okay, then then CuNiFe alloys. Okay, then carbon steel, etc., etc. Okay, acha, then soft magnetic material. Soft magnetic material, where are soft magnetic material used? Soft magnetic material, again, low retentivity, low coercivity. Okay, low retentivity, low coercivity. Okay, so means where can you use this? So they can be easily magnetized, easily demagnetized. Okay, so where can you use this? You can use in you can use this in devices, in high frequency devices, in high frequency devices. You can use this in high frequency devices. Okay, like high frequency devices you can use it, like transformer core, chokes. Okay, to why? To reduce the AD current loss, Okay, then in antennas, they can be used in antenna. Okay, then they can be used in TV transformer, audio and TV transformer, audio and TV transformer. Okay, these are the examples of soft. Example of soft magnetic material. Example of soft material are your mild steel, or say palm alloy. Okay, palm alloy. What is palm alloy? 55 Fe, 45 Ni. Then magnetic mild steel, Okay, magnetic mild steel, etc. Okay, so these are the things. These are the examples of soft magnetic material. Now, um, nickel zinc ferrite is also okay. Oh, I didn't show it here. Okay, now I think you can see. So nickel zinc ferrite, I'll come to ferrite just after this. Nickel zinc ferrite is also a soft magnetic material. Nickel zinc ferrite is also a soft magnetic material. Okay, now let us come to our next portion, that is antiferromagnetic material. Antiferromagnetic material. Okay, so what are antiferromagnetic materials? Example are oxides. Okay, oxides. What are those oxides? FeO, MnO, FeCl2, then NiCl2. Okay, so here what do you see here? Basically there are two two atoms, like here iron oxygen, manganese oxygen, and here iron chlorine, like this. So actually the two lattices are there where the spins are arranged in this way, actually equal and opposite, equal and opposite, equal and opposite, like this. Okay, so basically the magnetization is cancelled. Okay, so here also, like I mean the susceptibility versus temperature, if you draw, the graph looks like this. This is called as the Néel temperature. Okay, Tn is called as the Néel temperature. What is the Néel temperature? Below the Néel temperature, the sample is antiferromagnetic. Okay, and above the Néel temperature, it is paramagnetic. Okay, so below Tn, the sample is antiferromagnetic, and above Tn, the sample is paramagnetic. Above Tn, the sample is paramagnetic. Okay, so this is the basically this not many things is there here. Okay, then comes here ferrimagnetic material. Ferrimagnetic material or ferrite. Ferrimagnetic material or ferrite. Okay, this is a very interesting type of element. This is I mean in a way similar to your ferromagnetism, and also similar to antiferromagnetism. How? Now here what happens, here the spins are arranged in this way, like this, and equal and not exactly opposite. Equal and opposite, sorry, equal and opposite, but not of same magnitude. Okay, equal and opposite but not of same magnitude, like this. Okay, for ferrimagnetic material, for ferrimagnetic material, the atomic dipole for ferromagnetic material, the atomic dipole in the upward direction, atomic dipole in the upward direction is not equal to the atomic dipole in the downward direction. In the downward direction. Okay, so there is a net magnetization in one direction. So there is a net magnetization in one direction. Okay, now what is the general formula of ferrites? What is the general formula of ferrites? The general formula of ferrites is basically it is XO Fe2O3, XO Fe2O3, where X stands for cobalt, nickel, iron, okay, copper, etc. Divalent metals, divalent elements. Okay, so what are the examples? If you take nickel, what will you get? You will get NiFe2O4. If you take copper, what it will be? CoFe2O4. If you take Fe, it will be Fe3O4. This is nickel ferrite. This is nickel ferrite. This is cobalt ferrite. This is magnetite. This is magnetite. Okay, this is nickel ferrite. This is cobalt ferrite. Okay, so now why this ferrite? Okay, application of ferrite. Application of ferrite. Okay, application of ferrite. So main properties of ferrites are what? Main